So next we're going to have, welcome back everyone. So next we're going to have Penny presenting some benchmarking and model intercomparison from the models that you've just heard. So off you go.
Okay, so when we talk about benchmarking, we generally mean two separate things. The first is when you code up someone else's model, as many of us have done, you want to check that your model matches their published version. And that generally, as Chen said, you find a figure or you find some data and you keep tweaking and you check you've interpreted the equations right until you can match it. And this takes a lot of time. And then there's a second type of benchmarking, which is what we're going to focus on today. And that is taking different models and running them for the same composition, the same oxygen fugacity, and seeing how they compare. And this is really valuable as well, because when you're working in igneous systems, you have to choose a model. So you want to know how much that model choice affects your calculations. So what we did is we sent 4 different melt compositions to everyone involved here and asked them to send their model results back so we could compare them. So to start with, we looked at saturation pressures. So this is assuming you have melting fusion, say. So we sent them a mold composition with a set major element content. We said we had 0.28% water, we have 1,100 ppm CO2, 1,400 ppm sulfur, and this is what the saturation pressures came out as. So the first 4 models are from VESIcal, and then we have Airy's model and Chen's model. And what I've done is I've also shown MOHO depth compilation globally as these black crosses. And these are not insignificant differences. If you were to run Dixon on a set of melting fusions, you would get about 1.3 kilobars. And if you were to run magmasat, you would get more like 2.4 kilobars. That's almost a factor of 2 difference. So this is something we really need to think about when we're using these models is, are we sure which model is best? And if we're not, this is probably the true uncertainty in many cases on our pressures. So that was MORB. All these models should really be calibrated for MORB. This is not pushing the calibration range in any way, shape or form. We also looked at an arc magma from Fuego. So again, relatively low silica content within the calibration range of the models. Quite a lot of sulfur this time, quite a lot of water and CO2. And you can see as a percentage, these are less different. This is more like kind of a 30% difference, but it's still significant that Shishkina ends up much deeper than, say, a Iacono-Marziano or the Chen's model. So again, in terms of arcs, this is your MOHO down here. These do have different volcanological interpretations in terms of what these results actually mean. We then look at a Rheolite, and this is kind of pushing it. So we have 2 models in VESIcal that are truly calibrated at a Rheolite, that is the Liu Rheolite model and magmasat. And this kind of shows as you push models outside their calibration ranges, you end up getting much more different results. So for example, if you ran Iacono-Marziano on a Rheolite, you would end up with a pressure up to 4 times deeper than using like a Rheolite specific model. So this is why, again, it's really important to make sure you're using them inside their calibration range. Sulfuri Hills was another comparison we did. So this is kind of in between the basalt and the Rhyolite end member. This is a dacitic magma. And you can see there are some pretty big differences here again, up to a factor of 3 in terms of pressure and depth in what you would calculate. And when you start getting these differences, you really need to start looking at the calibration data set. So for example, we can see here that Iacono-Marziano is quite a bit lower than magmasat. And this is actually a single Sulfuri Hills melting fusion from Mike Cassidy. What we can do is we can plot all of the melting fusions. And what I'm basically showing here is the difference in saturation pressure between Iacono-Marziano and magmasat as a function of the silica content. Now, there's 2 slightly different versions of these models, whether you use hydrous or anhydrous coefficients. Most people use this model with the hydrous coefficients. And you can see as you increase silica content, so as you get more and more outside the calibration range of this model, this discrepancy just goes really, really big. You end up with a factor of 4 or 5 times difference in your saturation pressures. So when you see a difference like this, one of the things you can do, and one of the things VESIcal allows us to do, is grab the calibration data set. So one of the key parameters for CO2 and water solubility in Iacono-Marziano is this NB/O parameter, so the number of non-bridging oxygens in the melt. And the calibration data set looks like this. And these melt inclusions from Sulfate Hills look like this. So you can see the one melt inclusion we chose at about 60 weight% silica isn't too far out, which is why there was only that factor of 2 difference. But if we had run this 65 or 70 weight% silica, you end up with really, really different results. And it is an empirical model, and you are extrapolating it beyond the calibration range. As you drop MbO, you drop water and CO2 solubility, and therefore you need a higher pressure to explain the amount of volatiles that you've measured in your melt inclusion. So what we would always advise is, if you're not really sure which model to use, calculate it for all of them. Now we have these easy to calculate tools. That's not that big an investment compared to like a standard melt inclusion workflow anyway. And so for example, for Sulfate Hills, we're basically plotting a cumulative density function where each line is a model and each step up is a melt inclusion. And here you can really see that Jacono Marziano is way off from all of the other models, and it would actually put you as being stored below the MOHO. So this is a great way to compare saturation pressures for melt inclusions. Now I'm going to talk slightly about the degassing path. So we also asked everyone to run a degassing path for this more magma. Now VESIcal doesn't do sulfur, so it only appears in the models, in VESIcal only appear in the water and CO2 space. So you can see sulfur is pretty different. And this is because Chen's model is actually saturating sulfide. So until you start degassing from about 200 MPa to about 30, that line is being controlled by the SCSS, not the degassing part. Whereas Airy and Echo's model have not saturated sulfide in this particular example. So that explains that different behavior. Water solubility is really similar between all the models. This is what we see again and again. Water solubility isn't that sensitive to melt composition, and that means the different parameterizations of the models do not make that much difference. Water CO2 space, again, you can't really see much difference because the water is kind of the main thing that's controlling that tick point, and that is all similar. But CO2 is quite different. You see that magmasat and say Dixon, which is this blue line, do show quite different results. And this is, you can see the main thing that is controlling what these lines look like is the saturation pressure. So these are the saturation pressures we showed before. So magmasat starts degassing much deeper, so the line is shifted right, whereas Dixon starts degassing much shallower. So that is what's kind of causing the spread out. Most of the changes in saturation pressure are caused by CO2 solubility because it's the most sensitive to melt composition. It's the one that all of the different parameterizations of the models differ the most. We look at fuego and it starts to get a lot more different. For sulfur, again, we see this lower sulfur content in the model which has saturated sulfides compared to these other two models which have not. Water is starting to spread out, and that's because we have much higher water content, so the percent differences, they become more apparent on these graphs. CO2 is starting to show a lot of divergence as well. So again, that Shishkina model is showing much, much higher pressures of your degassing initiating. And you can start to see this in the water CO2 plot. You get slightly different slopes. But again, overlaying this on melt inclusion data is not going to look that different in this bottom right. So again, the main thing that's controlling these differences is whether or not you're saturating sulfide, and your CO2 model, which is the main thing controlling the pressure differences between these different models. Sulfate Hills is the most different. So getting to even higher silica content, we're pushing the calibration range of a lot of these models. You can see massive differences in sulfur behavior. So Chen's model is degassing sulfur much, much earlier, whereas Airy and Echo's model are showing pretty similar results. The water behavior starts to diverge massively. The models which rely on Jacono Marziano are well outside of this NB/O parameter, and they end up predicting very, very different results to the other models. You can see CO2 solubility is also drastically different at this point, and this is again reflecting the differences in the saturation pressure where you're initiating the model, and just the fact that melt composition affects CO2 solubility so dramatically. And that is causing spread out in your water and CO2. So these model differences really start to get concerning when you look at magmas like Sulfate Hills. It is very hard to know which of these models you would want to trust to compare your melt inclusions or your gas data to. So degassing ratios was another thing we looked at. So we're basically calculating the CO2 over sulfur ratio, and we're actually doing this as sulfur total. So we're adding up all of the different sulfur species. So it's not SO2, but commonly this is expressed in the literature where sulfur total is SO2. So for MORB, these look pretty different at all pressures, but it's worth recognizing that above about 100, this is just like a high ratio. It's whether, you have 1% SO2 or 0.25% SO2. So these aren't that different in that they're all very big numbers. The differences really start to come in once you actually start degassing sulfur. So about 50 MPa, these are actually the noticeable differences between these models. And we can kind of examine this more by looking at the sulfur pressure space. So we see, let's compare, for example, ERI's model to ECHO's, because these two models kind of show similar behavior, and this one is deviating. You can see sulfur X begins to degas sulfur much earlier. So that basically means you end up diving down below ERI's model, and ERI's model only starts this dive down, i.e. the denominator increasing, so SO2 in the fluid increasing much, much, much later. CO2 behavior is reasonably similar in these models. So it's really being controlled by the point at which sulfur begins to degas. For Fuego, they actually show similar trends. The ratios are slightly different, but there's none of this like contrasting direction that we see. And then Sulfuri Hills, perhaps unsurprisingly, shows very different behavior. So you can see these two models are kind of, so ERI and ECHO's model, very steep drop down, high ratios above 1. Chen's model is pretty much flat and just below 1. So again, we can understand this a bit by looking at the concentration in the melt versus the pressure, so the degassing paths. And you can see in Chen's model, originally the SO2, which is the solid line, drops a lot faster than the CO2. So that means you end up with a high denominator, so a ratio less than 1. Whereas in ERI and ECHO's model, you are dropping CO2, so these dashed lines, much, much more quickly than SO2. So that ends up giving you a higher ratio. So this is concerning because people have used CO2 SO2 as a barometer. And the question is it based on these model discrepancies? So for MORB, or say for Fuego to start with, you're going to get, say you measure a CO2 SO2 ratio of 5, you're going to get a pressure of about 250 MPa using ERI's model or 450 using Chen's model. For MORB, say you measured a ratio of 100. For ERI's model, you would be up at 250. For these others, you would be at about 550 to 70. So that's a huge difference again. And for Sulfuri Hills, say you measure this gas ratio, you will not even get a solution for ERI and ECHO's model, or vice versa. If that ratio is higher, only 2 of the models would give you a solution, not 3. So this is definitely something we need to think about. And same SO2 over sulfur total also shows pretty big differences for all 3 compositions for these models. So in general, it's really, really important to do these comparisons. The biggest problem when doing this is that it's hard to compare outputs. This is a time-consuming thing to do. So these are the 3 outputs I gathered for sulfur. You can see all of the column headings are different. The formatting is different. It's hard to sort of automate this in any sensible way without renaming all of the columns automatically. And then there's just a lot of ambiguities in how we write expressions in our papers that makes it hard to compare. So I'll just quickly show an example of this for the sulfate capacity. So Hugh O'Neill and Julian Booling and Wood produced a expression for both of these coming out the same year. So this is the amount of capacity of sulfur 6+. You can see this top expression says XMG, and the bottom expression has X in terms of the oxide. And these authors actually thought they were using different terms, but these are both cation fractions, and this can make it really confusing to compare. There's also, these are not actually directly comparable. You cannot just exponent 1 and do 10 to the power to compare them. They're actually looking at different equilibrium and different, one's in ppm and one's in weight %. So it is very, very hard to compare these models. And that's why having some sort of coherent community structure would make that a lot easier, because otherwise you spend days digging into this stuff to try and work out why one log value doesn't compare to another in another model. So with that, I'm happy to take any questions. Obviously, that was a bit of a brief tour, but these were the results we pulled together in the last few days.
Any quick questions? Can VESIcal output graphical representations of analytical uncertainty?
What do you mean by do you mean like your SIMS measurements of water and CO2, or do you mean like of the model uncertainty? The model uncertainty is really hard. It's not said in a lot of papers. A lot of people just say it's like approximately 20% for pure water or pure CO2. But that, like, obviously, we'll talk about this in a minute. Once you get to mixed fluids, those errors compound in ways we don't truly understand. So I actually think getting a handle on the errors of the different models is something that's very challenging right now. And if anyone else wants to cut in with that.
Just chime in, yeah, in agreement with Penny that we spent a lot of time talking about how to implement this, and that is the issue, is that a lot of people don't report errors at all, and if they do, they're not consistent or propagated. And we would have had to choose for the authors how to implement an error strategy that would kind of be consistent throughout all the different models, and we figured that wasn't something sort of scientific to do. So we waited on that and instead give you their recommended ranges for parameter space is what we decided on in the end for now.
Cool. I think with that, I'll hand over to Tyler for chairing the first of our discussion parts.